What is the minimum energy required to launch a satellite of mass small m from the surface of a planet of mass capital M and radius capital R into a circular orbit at an altitude of 2 capital R? So for a circular orbit, we have the required centripetal force is equal to the mass of the satellite multiplied by the square of the velocity of the satellite divided by the radius of the orbit. In this case, the radius of the orbit is equal to 3r. Why 3r? Because the radius of the planet is capital R and the altitude of the orbit above the surface is 2r. This is provided by the gravitational force, which has a magnitude of g capital M small m by the square of the radius of the orbit. Some terms here cancel out and we have v square is equal to g capital M by 3r. Now the potential energy of any gravitational field is given by potential energy is equal to the negative of g capital M small m divided by small r, where small r represents the separation between the two bodies, and hence the change in potential energy from the surface to the circular orbit would be equal to the final potential energy minus gmm by 3r minus the initial potential energy, which is minus gmm by r. So this turns out to be gmm by r into 2 by 3. Also, after taking the satellite to an altitude of 2r or to the radius of 3r, we also need to impart this amount of velocity to it. Therefore, the amount of kinetic energy added to the satellite would be equal to 1 by 2 small m into v square, and v square is gm by 3r. Hence, the total energy that is imparted to the satellite is equal to the change in potential energy plus the change in kinetic energy. So we can write this as g capital M small m by capital R multiplied by 2 by 3 plus 1 by 6, or 5 by 6 g capital M small m by capital R, and hence option A is the answer.